did I get your title right, Tim?
Academic and Student Affairs, yes.
Academic and Student Affairs, right. And he's also, I would guess, perhaps the founding member of our natural language processing department, really a pivotal figure here at MBZUAI. And he's going to be giving his talk on AI ecosystems, the case for natural language modeling.
Thank you. Sorry, I'll just share my screen again. You can see the slides okay? Okay.
We can see it. So
you can see the slides okay?
Yeah, it's okay.
Excellent. Okay. So apologies for doing this virtually rather than in person. I come to you from South Korea in a very historic temple right near Gyeongju down in the southeast. I'm here for a conference for colleagues, so a slightly surreal atmosphere to be giving a technical talk, but bear with me. So what I wanted to do in this talk was give you a bit of an overview of natural language processing. Being mindful of the talk just now that I got the tail end of was talking about birds. So you've obviously been exposed to some of the concepts that I'm going to be presenting here. And so I'll do this in two major parts, a bit of a background on how modern day NLP works, the sorts of models that we use, how we train those models, and what the implications then are for the ecosystem, and then talk a little bit about model sharing and modern NLP paradigms and implications for open source and the broader ecosystem. So just as framing remarks, I'm not attempting in this short 15-minute talk to tell you everything there is to know about modern day NLP. It's sort of very shallow and broad, with a focus on the ecosystem, no squiggles, no algorithmic details, lots of hand waviness in terms of the intuitions, but hopefully it gives you a better sense, I guess, of where NLP is actually. So natural language processing, as hopefully you're aware, is all about processing of text. So it focused on the fact that much of the archived human output, as in direct archived human output for different cultures, is in written language. And different languages have developed different writing systems. Examples, the Rosetta Stone on the left here, and one of the first Japanese novels that's still in existence called The Tale of Genji on the right. Of course, there are lots of languages without writing systems, but I'm focusing on those with here. So given the central place that text has for not just communication, but archiving, particularly for more formal purposes, whether that be technical documents, as this audience is very familiar with legal contracts, legislation, scientifically speaking, when we publish our work, it's very much in text, which is a slight oddity when you think about it, because it's such an imprecise medium in which to present such deep conceptual ideas. So NLP is all about extracting knowledge from that text or converting it into a form that's actionable, whatever that means. So as examples of that, coming back to our example of the Tale of Genji, it could be in the top right here, machine translation, say, taking the original Japanese and translating it into English, or in the bottom right, something like dependency parsing or some form of information extraction, capturing the fact that in this opening sentence of the Tale of Genji, the emperor loved a lady. So surfacing the latent semantic structure of the text. So I'm sure many of you have heard this term large language model. So nowadays, much of NLP is based on large language models for all sorts of NLP applications. I've just given you a sort of broad spectrum of different styles of NLP application here to give you a sense. So anything from sequence tagging, find all of the people mentioned in a given document for a service like LinkedIn, say, document classification, so document label labeling, is it spam or is it not, say, for an email provider, machine translation, as we saw in the example just now, summarization, so take a single document or multiple documents and distill them into some shorter textual summary. Image captioning, so it doesn't have to be text to text or text to structured or semi-structured representation. So nowadays there's more and more at the interface with text and different modalities like images and speech, obviously, I guess. So what is a large language model? How do we train? So the two major components are representation learning, which is a fancy way to say that we're projecting words or fragments of language onto what's traditionally nowadays dense vectors. So think of that as a list of floats, or a dense vector of real numbers, depending on whether you're more computer science or mathematically inclined, also called an embedding. So people often talk about embedding learning, word embeddings or document embeddings. So that's the first part. So that's what we're trying to translate text into and from, as we'll see in a moment. The second part is what's called pre-training. And the key idea here is using what's called self-supervision. So the self there is, it's supervised, but we don't rely on any external labeling. We're deriving labels based on the raw text in the form of tasks such as what we have depicted in the bottom of this slide. Like I'm masking, as in hiding a word within a particular context, and I'm trying to get a model to predict what is the word that I have masked. So in this example, in the top example, the cat something on the obvious candidate there would be something like sat or slept or something like that, some verb. Or in the bottom example, rather than taking context and predicting a single word, we're taking a single word and predicting the contextual words around it. And this is a particular instance of a very early example, as in all of 9 years ago, but in terms of large language models, very early, called word2vec, which people may have heard of. So the more modern methods, it's harder to describe. So let me just, in the context of the sort of now very much outdated word2vec, just give you a bit of a sense in how these models are pre-trained. So in the first example, where we've got the cat, a masked word on the, and we're trying to predict what that word is, we do something like this, where the representations we have for each of our context words is an embedding, as we said before, so a vector of real numbers. We have some method of aggregating over those. In the case of the placebo model, it's a simple summation across the individual values. And then we have prediction that we're doing off the representation, the aggregated representation that we generate there, using something like a sigmoid, say, where we want to be able to predict sat or whatever it is in this particular context. Let's assume it's a sat with high confidence and anything else with low confidence. And so we have some learning objective which encourages that behavior. And in performing this pre-training across lots of data, we learn these representations which maximize the predictability of or recoverability of these masked words. So nowadays, very few people play around with word2vec. It's all about transformer-based models. And I'm not going to go into what a transformer is. That would take a lot longer than just the 15 minutes. But BERT we had mentioned before. So BERT, it's all of 3 years old, but it sort of, given how rapidly things are moving, it sort of feels like an old model nowadays. But a lot of the work is styled around BERT. So I'll sort of describe the very basics of BERT to give you a feel for it. So in the case of BERT, we have a similar objective in terms of the masked language model objective, except that instead of for a fixed context, such as 2 words to either side of a word, predict the masked word, I've got some variable width context, and I'm doing stochastic masking, as in I have some random variable, some hyperparameter in terms of the proportion of words and the prior for masking a given word. And across different passes of pre-training, I'm going to be predicting different masked words in the same context, with the important differentiation over word2vec, that these are going to be contextualized in a given context. The representation that I would generate for the same token is going to be very different. Whereas in the word to vec case, it's a word embedding. So I will generate a single representation, a single embedding for a given word aggregated across all of the occurrences of that. So mass language modeling is sort of the basic, the absolute sort of bread and butter of modern day large language models. And then different language models have different secondary objectives. They often combine. The original BERT had something called next sentence prediction, where you had a concatenation of two sentences, and the simple task is, does B follow A as a sentence? And the important thing to note here is these special tokens that we have. So we've got our first sentence and this SEP token, the second sentence with a SEP token. So we're injecting structure through the use of these special status tokens and attuning the model to the fact that we're actually, we've got in this particular case, two sentences, and in other cases, maybe we'll have more than two sentences. We can have other special status tokens to represent different structures. So that's sort of the very basics, and BERT is an example of something called an encoder model. So through this pre-training, largely based on mass language modeling, what we're doing is taking different contexts and generating representations. And in practice, we're generating individual contextual representations for each of the tokens, as well as an overall representation, which is canonically associated with this special CLS token that as the starting token. But it's an encoder in the sense that we take text and we generate these embeddings for the text, for individual tokens as well as overall. We also have two other key flavors of modern day large language model. So an encoder decoder, if you look at the way it's presented here, it sort of looks trivial. So it's what's called an autoencoder. In which we're projecting a given sentence as well as each of the individual tokens into a given embedding, and then from that embedding we're trying to reproduce the original sentence. So we've got this information bottleneck in terms of how we train our model. And of course, you can train this simplistically in terms of recover the original text. The real power comes when you then take the pre-trained model and fine-tune it to do all sorts of other tasks like machine translation, where it's not the original sentence in the same sentence, or perhaps to a paraphrase of that, it's an English sentence to a Korean sentence, for example. Then the last example is a little bit dumbed down here, but just to give you an idea, it's what's called a decoder-only model, where classically it's something like an autoregressive language model, where we're predicting, given a particular context, what is the next word to occur. So rather than I give you the full context and mask tokens, I want you to reproduce the mask tokens, it's an open-ended task in that I want you to continue on from what I've got here. So in terms of the models that you've perhaps heard of, BERT is an encoder, something like BART or T5 are encoder decoders, and GPT-3, for example, is a decoder. Okay, so that's sort of the very basics of NLP 101. So given that, then pre-trained language models are very much at the core of the modern day NLP paradigm, in that kind of the recipe to perform a large variety of NLP tasks, as we had in the earlier slide, is you go to Hugging Face or whatever your favorite repository of different large language models is, you download a model, you optionally do some what's called adaptive pre-training, as in you do more of the pre-training on some domain-specific text to better attune it to that particular text. And if you're doing something like legal text processing, say, you then fine-tune it. So the adaptive pre-training is just more whatever, mass language modeling, for example. So this idea of self-supervision. The fine-tuning is where we've actually got labels which are specific to whatever the task is that we're trying to perform. So something like document level classification, if we're doing spam filtering, say. So we're actually trying to predict those specific labels to specialize our model to perform that particular task on the basis of the substrate large language model. And then, of course, we perform inference over whatever our data of interest is. So I promised to talk about the NLP ecosystem. Given the fact that large language models are sort of very much at the core of modern day NLP, there's a very strong fixation on large language models, as you would expect. And so there's a very strong culture nowadays of particularly the big tech companies and to a lesser degree, large research organizations like Allen AI, say, to release these large language models. So BERT came from Google, for example, BART came from what was FAIR, what's now MBZUAI, Amazon's in the game, lots of Huawei, it's not specifically US, of course, release these different language models. And part of the motivation there, beyond some PR purposes, is to accelerate NLP research. Because once you've got one of these models and are doing the fine tuning, yes, there's some cost there, but most of the cost comes in the pre-training. So GPT-3, I will come to a little bit later. I don't have here because it's not a public domain model, but estimates of the cost to do a pre-training of a GPT-3 from scratch. At the time it was trained, at least, it's in the tens of millions of dollars of compute time. They're not something that you want individual organizations to have to go through themselves. Licensing is interesting. Different organizations have very different philosophies in terms of licensing. So models like BERT, say, were released under very permissive licenses and had a lot of impact because of that. Some of the other ones under commercial or non-commercial licensing. That's a topic for another day. That's a little bit of an aside, a little bit of a case study that I wanted to mention, partly to reflect on this sort of question of ecosystem and sharing of models. So OpenAI is kind of the elephant in the room here that I hadn't mentioned, that has released GPT-3, for example, who have used a very different paradigm of trying to monetize large language models, with some success, to be fair. I'm not trying to criticize OpenAI, but so rather than releasing the model, they've made GPT-3 available on a paid basis for organizations to be able to play around, including being able to do fine tuning of the GPT-3 model. And as a result, GPT-3 in research circles has had much less impact than some of the other models, simply because you can't download it and play around with it and build on top of it. And kind of a very recent exemplar of that is in the context of text to image. So generate an image given a textual description. So I've got here some exemplars from DALL-E 2 from OpenAI versus Stable Diffusion. I'm sure you've seen various examples of these over the last couple of months. They've kind of been doing the rounds on social media. So I sort of did the obligatory generation for the prompt AI researcher on a bicycle. DALL-E 2 has been a lab coat. I'm a big cyclist, just as background. Stable Diffusion is sort of very much more the tech pro look, I guess, with a slightly weird handlebar, but impressive that just given that prompt, it can generate these images, and it obviously has its own ideas about what AI researchers look like. The point here, though, is a perhaps unsurprising but fascinating thing that's happened is Stable Diffusion was released by Stability.ai, I hadn't mentioned, but was in the previous slide, a month after DALL-E 2, which made a big splash when it was first released about 2 months ago. What's happened since it was released, though, is remarkable, in that all sorts of applications have been developed in a very short time for Blender, for example, in terms of a shader editor for gaming purposes, for Cinema 4D in terms of some photorealistic graphical rendering, for Photoshop, for in-painting and out-painting, for Canva, for graphic design purposes and various other things. And so the list goes on. Because it's been released into the public domain in downloadable form. Whereas for DALL-E 2, there's nothing. You don't have all of these innovative applications that are built on top of it because you can't access it as a standalone model. You can only play around with it in very limited means via the API or through the web interface. So I'm possibly getting to the end of my time, but I want to just spend a little bit of time talking about some of the limitations of current NLP research. It's certainly not the case that large language models solve everything, but because of this strong fixation on large language models, there's an assumption that's sort of built into a lot of work nowadays that you can access a large language model for a particular language for a particular purpose and get task-specific training data. That's obviously not the case all the time, particularly if you're looking at lower resource languages or sort of very specific text processing tasks where there are perhaps privacy concerns or legal concerns in terms of getting access to data. Also, I guess just a lot of classification work. The label set is fixed, predetermined, a priori, which if you're doing a more exploratory task, maybe you know something about the sorts of labels you want to use, but you actually want to learn some of the labels along the way. That's much harder. It's a little bit of sort of artificial task definitions, possibly kidding ourselves about what a task really should look like to make it easier to progress research. So an example of that would be question answering, where a lot of the research nowadays is squad style. I'm giving you a paragraph from Wikipedia, say, answer it relative to that, rather than I don't know where the answer is, go and find it yourself. There's a retrieval question and a very real likelihood that there's not a single text that actually contains the answer that you're after. Or maybe it's completely unanswerable. Large fixation on either single or paired document classification or regression problems, or string-to-string translation of sequence labeling. Strong fixation on English. There's a very sharp drop-off for other languages. Documents you want to have reasonable length, so you've got enough context, but not too much. You can't fit them into the input of your large language model. So if the text is too long, you've got problems. If it's too short, you've got problems. There's kind of a Goldilocks length that you're after. A lot of the tasks we still perform at the sentence level for things like machine translation, say you don't do it at the document level, so that has implications for the coherence of a document level translation. Say text is clean and homogeneous. Twitter is obviously not a safe place for NLP. And this is possibly less of an assumption nowadays. Things are getting more and more multimodal, as we had in the case of stable diffusion, for example. But there's still a sort of strong fixation on text to the exclusion of other modalities, unsurprisingly. Evaluation, not sort of in terms of user experience or sort of cost of error, kind of embedded evaluation in terms of specific tasks. So kind of test tube evaluation still. And, IID assumptions and assumptions that there's no temporal shift in the data, which causes all sorts of havoc in real-time applications where if you've got a trained model from 12 months ago, even potentially the stream of data that you're seeing now is very different to what the model is trained over. So I suspect I'm running out of time. Let me just very quickly wrap up. So modern day NLP is dominated by large language models. Hopefully you've got a bit of a sense on the basis of this talk of what I mean by a large language model. And this paradigm of pre-train over some textual corpus and then fine-tune to a specific task. Lots of pre-training, a lot less fine-tuning. A lot of the acceleration has been driven by not just the fact that we have large language models, but they've been released into the wild, particularly for research purposes. So the sharp uptick that we've seen in performance over different tasks, a lot of it has come from this sharing culture. And at the end, we talked a little bit about perhaps some of the myopia of NLP research. And that was all that I had to say. Thank you very much. Again, apologies for the slightly surreal setting.
Thank you so much, Tim. And I know normally it's our practice to leave the questions and discussions for the break, but logically, Tim will not be available during there. So I wanted to at least open up a few minutes in our schedule for the audience here, or some of the students that have just newly joined us, to ask any question you'd like to our speaker.
So the question is that not all the time we need to use this big language model. Sometimes maybe simple traditional models are already good enough. So is there a way that we can decide when to use the complicated resource consuming model, but when we don't need that?
Yes, so let me repeat the question. So I'll repeat the question so it's captured on the microphone. So Professor Chijan's question was, when should we be using the large models, or when is it preferable to use a simpler model? Is there a way for us to tell?
So it's an excellent question, very topical in NLP at the moment. I mean, a simple answer to that is, well, for languages where you don't have them, or for text types which are far removed from the sort of text that large language models tend to be trained over, which is things like dumps of Wikipedia and book or newspaper corpora, sort of fairly sort of general text. If it's sort of something very specialized, chances are the vocabulary is going to mismatch apart from anything else. So the tokenizer will be ill-fitting to what you're trying to do. I mean, another of the concerns is if you're in a context where you need to have high model reliability, as in you need to be sure of particular behaviors of the model. One of the risks, of course, with these large language models is, particularly if you have a 200 billion parameter model, like some of the recent Alex TM models, it's very hard to know what the model is doing. So providing sort of safety guarantees, say, is a very hard thing to do with large language models. So it's very much a use case based question, I think. But also large documents. So a lot of the legal NLP work, for example, it's the classic bag of words, TF-IDF weighted support vector machine models actually often do better than the large language models, just because they struggle to capture a 10,000 word document that has the full proceedings of a legal case. And
that answers Professor Chijan's question. Thank you, Tim. Any further questions from the audience? Okay, go ahead, Meron.
So I have a follow-up question. So do you think that in this safety critical scenarios, language models have to be substituted with something else, or do you think there is a path for updating or changing or somehow using these large language models where safety is paramount?
So to repeat the question, Meron was asking about whether there are ways to incorporate language models in so-called critical situations where safety is paramount, or perhaps is that inadvisable? Maybe that's the other question.
Yes. So and there's a lot of work on doing post-processing or sort of post-training, I guess, as distinguished from pre-training of these large language models, consistent with the pre-training paradigm. To do things like better calibrate the model in terms of the probability distributions that it generates, or debias the models in different ways. And what you often find is, you can to some degree calibrate them and to some degree debias them, but they're such large models that it's hard to do it post hoc. So what we really need to do is embed some of these methods, depending on what the scenario and what dimension of safety it is you're interested in, as part of the pre-training regimen, so that you don't kind of have to mop things up after the fact, or sort of try to wrestle the model to perform in a sort of more predictable way. And that's very much an open research area.
Okay, I think with that, let's thank Tim again once more for the welcome.
Thank you very much, Kamsahamnida.